Hello, Sandy.
Yeah, bro,
Yeah,
record, sir.
Catherine.
Yes, yeah, hi, hi. So basically, I'll just give you a recap of what I did covered in last class, and then I'll further with this continue with the current class that I were going to cover. So we discussed on Spark architecture. So and then inside Spark architecture, I just started with the driver program, cluster manager, and then how each executor codes and how many number of worker nodes that we'll be deciding. And then I talked about Spark transformations and actions. Once after Spark transformations and actions are done, then I talked about lazy evaluation. So why Spark is called as lazy evaluation, and then we also talked about something graph called lineage graph, and we also cut out types of transformations, that is wide and narrow transformation, and we talked about the data structures, mainly data frame, data set, and RDD. uh, the sequence could be RDD, data frame, and data set. So we just talked about what is the difference and each thing. And today I'm just going to talk about mainly on executor tuning. So basically executor tuning, what exactly is executor tuning? And then, so basically whenever we are submitting any Spark job, so there will be a command which talks about a Spark submit parameter, which we'll be calling it as a Spark submit parameter. So basically it looks like Spark submit. So and then hyphen class name. So you'll be mentioning a class name, and then extension to that class name. You'll be having number of executors. So and next will be number of cores, and then driver memory, executor memory. And in addition to that, there are various parameters which one can be performed as per your executor tuning memory technique, or depending upon the shuffling technique that you want to use, you can make use of a shuffling parameters as well. So now I'm going to talk about some concept, mainly talks about how to come up with right number of executors. So right number of words, like basically how to come up with a number of executors that are suitable for our particular job that we are running, and how to come up with the number of executors required for our particular job, and how to come up with a driver memory, how to come up with executor memory in this particular thing. So there are three approaches. So basically whenever we are running as a data engineer, if you want to run it any particular job, there are three approaches basically one can use to run a particular job. So one approach that we will be mainly calling, that particular approach could be fat executors. So the purpose of fat executors is mainly is about, like, imagine I am running a small program like where my particular job required some 5 executors or 10 GB of driver memory, but uh, unknowingly you mentioned how many ever executors is available in the entire cluster. You just mentioned it. So in that case, your job will still run the entire process, but unnecessarily you are wasting the number of executors in the driver memory that you don't need it, because you're trying to take more resources than expected from the particular approach, from the particular number of available executors. So you are actually trying to make more number of executors even though that is not required for you. So that is one of the thing, like where you will be calling it as a fat executors. And coming to the minimum executors approach, so basically minimum executors is about, I'll give you an example. So I'm just giving you a theory about like what exactly is minimum executors. So minimum executors, as we know, every executor, that is every worker node, can have 5 parallel cores. What is the purpose of core? Core is basically a CPU actual unit where the actual work progressing will be done. So every worker node or executor can have 5 parallel cores. So as per the Databricks, because Spark developed the Databricks, so it's better every executor can have 5 cores. But imagine in minimum executors, I am using only one executor core, 1 core per executor. So in that case, your job will still your job will still try to complete it, but it will take ample amount of time rather than expected. So now, among all these two approaches, so which one to use? Either do I have to use fat executors or minimum executors approach? No, you're not supposed to use either of the one. We need to find out a particular approach which can be balanced in between both these fat executors and minimalistic executors, and then accordingly you will be able to implement implement the one that you want. So as per your particular executors. So now coming to the third approach. So the third approach could be, what is the best approach? So I have to use something balance between fat executors and minimalistic executors approach. So before going for this, in order to, let's try to understand, whenever we are configuring any Spark Submit particular parameter values, there are 4 thumb rules that everyone has to keep in mind, and then we'll be able to come up with a number of executors. So first thing, when you are running any particular job, right, it's not only about, you have to keep it in mind, right, for your particular program as part of our data engineering skills, there are some background daemons which are running. So the background daemons mainly as per Spark architecture and Hadoop architectures are name node, data node, secondary name node, cluster manager, resource manager. So these are the background daemons that we'll be running it. We won't be mentioning how much memory is required for this particular daemons as part of our Spark Submit program. So, but when you are constructing any particular executors, a number of cores or approach, you have to keep it in mind in such a way that keeping the background daemons as well. So for that purpose, we will leave one executor per core for background daemons. Leave one executor per core. So basically, if I am assigning 5 executors as part my Spark Submit program, out of 5, 1 core will be assigned internally by the inbuilt daemons, like mainly for operating system, name node, data node, for this particular thing. So, and only 4 parallel tasks will be run by our particular job. So how much ever we'll mention, if I mention number of executors as 10, cores has 10, each executor can have 10 cores. So in that case, only 9 will be used by our program, and the remaining 1 will be used by background daemons. So this is one particular thing that we have to leave leave one particular core per node. So if n number of nodes is there, so every node from, we have to leave one aside, one particular executors. So now the second thing could be, in a HDFS high throughput. So basically, the reason why I said like HDFS high throughput is, so basically whenever we are having 5 particular executor parallel tasks, so we should not, will be having not particular more than that. So because when, in order to achieve HDFS high throughput, so there is a certain criteria that where high throughput can be achieved only when you are having certain executors. So if you are using, if a particular Spark job has required 5 executors, but I am using 100 executors rather than this expected, in that case, your job will finish the task pretty much fastly. And in that particular scenarios, there might be a overburden on the garbage collection overheads. So this is the reason. So basically, GC is nothing but garbage collection overhead. So basically, then Spark came up in, the Spark Databricks said that it was observed, like whenever you are, if you want to achieve HDFS high throughput, you need to have somewhere close to 5 tasks per executor. So in order to achieve HDFS high throughput, so this is the second criteria. And the third criteria mainly we are talking about could be YARN application master. So basically, YARN stands for yet, Y stands for yet, A stands for another, R stands for resource, N stands for negotiator. So mainly, as I said in the Spark architecture, it is responsible for negotiating resources from cluster manager or the resource manager who actually has all the resources to execute and monitor for the containers for our particular jobs needed. So if we are basically using Spark on Yarn, then we have to ensure that every executor can have 1024 MB, that is 1 GB of memory per executor. So we have to have minimum of this particular memory in order to make use of this particular approach. So now the fourth approach could be, we have to keep it in mind that whenever you'll work in Spark, whenever you are running any job in Spark, so there will be a overheaded memory. Like if I'm requesting 10 GB of memory, I'll be getting might be somewhere around 11 GB or 12 GB or 13 GB of memory. So I'm getting some extra amount of memory even though I haven't requested. Why we are getting extra amount of memory even though you haven't requested? So that's because of a concept called memory overhead. So I'll just tell you how it works is basically. So I'll just give you an example like how memory overhead will work, and then accordingly you'll be able to understand more about how memory overhead will work. For example, if I give you an example, so remember, remember for my particular job, I required 20 GB of memory. So if I requested 20 GB of memory, what it will happen is 20 GB. So as I said in the Spark architecture, let me go to that architecture. Where was that? Able to understand it, right?
Yeah, it was in the Hadoop.
Okay. Yeah. So if I see here, so basically this is the what I'm talking about. So whenever we trigger any Spark Submit program, driver program is the first where it gets launched, and then it requests the cluster managers, and then the number of executors, and then inside each number of executor there will be a tasks which will be triggering upon, and then it will be running. So now what I'm talking about is for our particular memory to manage all these particular things. Remember, I have requested 20 GB of memory. I only need 20 GB of memory. But internally, for your program, you won't be getting only 20 GB of memory. So there will be a memory overhead of approach. So it will get 20 GB of memory plus 7% of memory that you requested. That is 20 GB. So 7% of 20 GB, it will be around 3 GB. So totally for your program, 23 GB of memory will be allocated as part of your program, as part of your particular program. So this we can control with a parameter mainly using spark.yarn.executor.memory overhead. So this is the default thing. We can't be able to change this particular thing. So in real time, what people do is, if you want to know the exact memory, this is default. This we are not doing explicitly. So automatically, if you request 20 GB, additionally 7 percentage of what you have requested will be calculated as part of this particular approach. So now I'll tell you the approach that we. So these are the 4 points that we will be keeping it in mind. So now I'll be talking some mathematical formulas that we'll be dealing with more oftenly, and I'll tell you how number of resources and number of cores will be getting launched. So as we know, we heard certain terms mainly till now in Spark program. We heard about driver program. That is driver where the what is this and executors, tasks, course. Course I said is about executor course. And next we talked about more about memory per executor. Okay. So now remember like for our particular, remember that cluster that every time I'm talking about cluster, right? Cluster is basically a place where it has how much memory is available in my entire cluster. So for our particular program which I am running, The cluster has below configuration. It says below, not between. So remember our application has 10 nodes. When I said about 10 nodes, this basically a data nodes. And each node has 16 cores. It means each node has 16 parallel processing tasks. Out of 16, as I said, one core per node will be used by background daemons. So 15 will be actually used by our particular program. So that everyone, we can only have an access to use maximum of 15 cores only. And next comes the memory. So I'm saying there is a 64 GB of memory available. This is per node. So totally it will be 10 into 64. That is 640 GB is available across all the nodes. So this is the configuration. So now if I talk about total cores, how many is total cores? Number of nodes, each node into each node has how many? 16 cores. So totally it will be 160 cores. Now total memory. How many nodes? 10. And each node has 64 GB. 10 into 64 comes around 640 GB of memory. Got it until clear, bro? Sister, if you have any doubt, you can just stop me and you can ask me right away. Or if I'm moving fast or pretty slow, you can just let me know.
No, you're good, but I just have a doubt about memory overload. Like you said, it will take 7% extra, right?
Okay, okay. So I'll tell you. I'll just cover in the end again. I'll just repeat it
Okay.
once again because I already started this. I mean, even in the end again, we'll subtract that. Sister, are you pretty much clear, sister, here? Or if you have any query?
I'm pretty much following up, yeah. But
Okay.
for now,
I'm
I'm good.
sorry. Yeah, I'm sorry when if I'm interacting. I mean, if I'm interrupting and asking that whether you are clear or not. So I'm
No,
just
that's fine.
yeah. So now, as we know, we calculated total course and this particular thing. So now, as per the Databricks, I said every Spark program that we are requested, you need to have 5 cores per node. So this is the thing that we know. So that is executor cores needs to be 5. So that this is as per the, there is no reason why are we making only 5. Nothing. Databricks, Spark developed a Databricks. So Databricks people suggested that if you want to achieve perform exactly parallel processing engine and make efficiently use of Spark, they mentioned that make use of 5 cores per node per executor so that you will be able to achieve better efficiency. So that is the reason we are using 5 cores here. So now I said we need to leave aside 1 core per executor. What is the reason why are we leaving 1 core per executor is mainly for background demands. So I mentioned in the earlier thing, background DAE. The term they use was demons, DAEMONS. So that is the thing. So now out of, if I leave out of 16, right? So out of 16, if I leave one, it will be 15 cores. The total cores available in my entire cluster will be only 15, not all, because one will be assigned each one of the background demons to assign for the particular job. So now, then total number of cores available will be 150 cores. If I leave one per particular per executors. So now the thing is in the in Spark architecture we have executors. How to come up with executors? This is a bit important. I mean this formula, like just be cautious and just, so number of available executors. So how will I get number of executors is total cores divided by number of cores per executor. So how much is total cores? 150. Sorry, 15 cores. Each particular thing has 5. Each particular thing 10 nodes, and it is 150 divided by, and how many cores per executor I have assigned over here? I assigned it as 5. So 150 divided by 5 comes at around 30 somewhere. I mean 150 by 30. So now here, if you talk about, like, I just used one particular executor, so totally there are 160 cores, and among 160, if you leave 1 core per background demands, it will be 15, and out of So total cores available in a cluster will be 150, 15 into 10, it will be 150. And number of executors that we are getting was 150 total cores divided by number of cores per executor. So that comes under around somewhere 150, somewhere, not somewhere, it's exactly 30. So now basically from one, if we leave one particular one executor per application manager. So until here it's clear how number of executors we got. Number of executors is nothing but the number of nodes that we will be mentioning in the Spark submit program, number of executors, this memory. So now I'll talk, now we are done with two parameters. We got number of cores, number of executors. Now the next thing that we will be calculating will be number of executors per node we got and memory per executor and driver memory. So this is the particular main thing that we'll calculate now. Okay, so now, so total number of executors is
These
30.
calculations are for per job, right? Or like
Yes.
for whole
No.
cluster
No. Per job. These
per
are at
job.
a per job level. Per job. If I am developing a particular job, you have to. So that at a cluster level, this is the thing. I just assume this is the cluster configuration. This will be constant all the time. So if I am one particular person who is running it, I'll be coming up with my own calculations of internal these things, and then I will be completing with that. And if Sunny wants to run another particular job, then he'll be coming up with his own calculation. And if another person own task, so in that particular thing we'll be able to get this particular number of cores. So but in real time now people, I mean only for experienced person like people will be, no one will be worrying more about what we are actually doing it. So we will be just copy pasting and trying to get a some random numbers, basically how much ever frequently which every person does that. So we'll just try to calculate that, but this is at a job level.
Okay. And um sorry, this
Yeah,
might sound stupid after all this,
no
but
worries.
where do we mention like how many nodes we are assigning for per job? Is it in the
Yes.
script or where do we
Yes, I mentioned you about one particular command, right? Which is called a
Spark.
Spark submit command parameter.
okay in
So
the
here,
Spark submit? Okay.
yeah. So here, if you see, when if you, I just mentioned this is the command which looks like. So I just mentioned it as number of executors. I gave question mark. So now here it comes five. Sorry, number of cores is five. Number of executors we got 30. So and driver memory I'll calculate now. Executor memory I'll calculate and show you. Now. That's the formula. So here we'll be mentioning.
Oh, got it, got it.
Okay. Okay. So now we got this particular thing. So now number of executors per node. So if we know number of executors are 30, that across all the nodes. Now I want to calculate how many executors per node it will be. So per node internally how many number of executors, that is number of executors divided by total nodes. Total nodes available in a cluster. So basically it will be 30 divided by 10, it will be 3. So now we will be having 3 executors per node level. Here I am talking about node, executor, cores. So these three guys. So
One
nodes,
quick
yeah,
question.
yes.
Um, Here we are mentioning like number of executors per node. That is,
Hmm.
do we are we configuring anywhere like this? Like, okay, these are the default executors per node. If we don't mention anything like that.
No, that by default, if you can randomly give some values by running the Spark submit parameter, if those many number of resources are available in a cluster, if none of them are running for your particular in a particular cluster, it will automatically, you can give any random values. So you might not be able to get any errors. When if there is sufficient memory and the number of resources available in the particular cluster, you can go ahead and you can run with any random things also. That won't cause any issue.
My question is there any default value like that, or if we don't mention it or something like that?
No. You
There
have to
is no
mention
default.
some value. There is no default
Okay.
value. When
Okay.
you are running this particular Spark parameter value, so you have to mention this particular value and you can run you have to run this value. I think if you didn't mention automatically, I think by default, how much ever memory will be, all the resources will be available, that particular things will be assigned as per the cluster level.
Okay, got it. That's what I'm asking you about.
Okay. So now how 30 came, we got it, right? Now I'll show you how much memory is required per executor. So now I'll memory per executor. So I mentioned as 64 GB per memory, 64 GB per node, and how many number of executors per node we calculate as 3. So 64 by 3, it comes around somewhere 21 GB. So this is the total memory required per executor level. So got it, total memory by number of how much memory got we got. So now, and for your question, Sunny, so in the end, remember, like now for my particular program, how much memory that I needed, how many I need, 30 executors, 5 cores per executor, and how much memory that I be needed. So here totally I got 21 GB memory, but I don't need the entire 21 GB. So internally, it might have calculated how much ever I needed plus 3 percentage of the memory that I want to for my Spark program. So if I take 3 percentage of this particular thing, so if you calculate 21 by 3 into 18, somewhere it comes around 7 percentage, 7 percentage of
7,
21 GB. Yeah, it will be
3.
uh, 18 GB plus 3 GB. So 18 will be 93 and this is 7 percentage. So total memory required by my Spark program is only 28 GB because internally it included the additional overhead heap memory as well, and then it calculated plus 7 percentage of my memory that is required. So this is the number of cores that needed by a Spark program to run my application. So number of executors, driver memory, and how many number of cores per executors. So this is the best approach. So every Spark application we will be calculating in this way. The calculation differs how much ever nodes that we are taking, how many ever number of cores that we are taking, and how much memory that we are taking. So this is the configuration. So you have to, so here if you see why I said here 5 per course, that's not only 5 guys, we can have any number. That's, I just said, like as per the data bricks, they said 5 cores per executor will be the best approach as per the data bricks, because Spark developed a data bricks. So that is the reason why why in a real time we'll use, but you might get more, but you have to calculate the memory as per this calculations level. Got it, brother?
Yeah, got it.
Hmm. So now, that is, I mean, just try to remember this calculation, and then because most probably for experienced candidates, right? I have faced this interview question multiple times. So they'll just ask about like if someone is more interested in terms of a configuration level. So basically, it will happen. So whenever we run any Spark job, right? So you might be able to see the job won't automatically enter into a running state. So basically, for every Spark program that we generate, it will come as application master, application 1 2 3 4 5 6 7, 1 2, this is application ID, and then accepted, accepted state. So why the jobs, the moment you run it, the jobs are in accepted state? Because the jobs are not getting enough resources from the cluster, because cluster might be busy with some other jobs. So after certain period of time, the job will enter into a running state, because the other jobs has finished their task and the resources has been released by the other jobs. Then those particular resources will be assigned back to your job. So that is why the job is went into a running state. So now to ensure that in the beginning itself, how can I overcome my job won't go to the accepted state? You have to check how much memory is available before running before running your job. Tweak your executors as per this calculation, then run your program. Your job won't go into accepted state at all. So that is the main key difference. Got it?
Yeah.
Okay. So sister, you can have any questions, you can just ask me, or even Sunny, you can do too, bro. So now let me talk about data structures that we have using more oftenly in Spark. So the three data structures that we are using more oftenly was RDD, data frame, and dataset. So what are these three? So every data structure that we are using it. So in other programming languages, if we use in Python, so you'll be having a data structures mainly list, tuple, hash map, hash, dictionary, set, and even the data types as well. So here in Spark, we have this, these are the data structures that is available. So now when to use RDD, this is one of the question, like you can, how to create an RDD, but basically how to create RDD. So before answering this, what is RDD? So RDD stands for Resilient Distributed Dataset. So I'll just explain you the resilient. So what is the purpose of resilient? Resilient means once you create any data mapping with RDD, you can't change it. So the transformations that will be stored in the form of a lineage graph, you can't modify them modify that. So it won't be halted it. So whenever you created any transformations, because RDD Spark is in lazy evaluation, so it will create this particular value. So resilient is the meaning stands for once an RDD is created, it is immutable. That is the main property, that is the best property you can say. So immutable. So in future, if there is any data loss, with the help of the lineage graph, we will be able to retrieve the data back with the help of lineage graph. So that is the purpose of immutability or resilient. Distributed, we know Spark works in a distributed framework, which splits the data and makes use of a parallelized framework. And resilient distributed data set. So data set is about the data structure, like which makes use of data structures to store the values about type safety and type conversion values. Now, how to create an RDD? So RDD can be created in three ways. One is using text file approach, that is text file method. Another one is using parallelized method. Third method could be using transformations. So how to use text file? So you might have seen, right? Every time whenever we are dealing with this, you'll be having an option sc.textfile path. So what is SC? SC is a Spark context variable which is available in the form of an SC from Spark by default. So this is how we'll, and when is parallelized is also the other method to create an custom RDD and using transformations. Last time when I said I gave you an example of how custom transformations looks like, right? So basically every transformations will be created lazy evaluation. So all the transformations will be stored in the form of a lineage graph until and unless you call an action, the entire process won't get executed. So every transformation we are creating a new thing. So that is why using transformation. So these are the three ways how we can create an RDD. And now, so using RDD, you have to mention the schema manually. It means it doesn't infer the schema automatically. You have to explicitly mention the schema. So it's mainly used when you have a data in the form of an unstructured data, basically, because it won't infer the schema automatically. So user has to specify the data explicitly for a column table data that we are using it. And so this is the one thing. And next comes data frame. So data frame is almost an equivalent table in MySQL relational databases table, so which stores the data in the form of a rows and columns. Since it stores the data in the form of a rows and columns, you need not to explicitly mention the schema, because automatically it has a column header and it will be able to read the data. It will be able to perform all the operations that it wants it. And next comes the, so these are the main, I'll share you a link for this particular thing. So because you just need to know about how to create an RDD, how to create a data set and data frame RDDs. It's all about theory only. It's about, if I talk, it will be much more boring sessions, boring rather than if I talk about. So just refer in the document. So if you have any queries, then I'll talk about. But this is also one of the important question, guys, in terms of an interview. So we'll have some optimization techniques. So among all these things, which is better? One thing, every task can be achieved by all the three. So depending upon your requirement, if you know the schema automatically, if you know the schema previously, go for data frame. If you didn't know the schema, you have to explicitly mention the schema by using RDD. And in this way, we will be able to infer this particular schema and you will be able to achieve all the operations that you want using data frame, dataset, and RDD. Okay. So now, Sunny, any doubt, or sister, if you have any query, you can just ask me.
Uh, I don't have any, but uh, as I like I didn't previously know about these data sets, and also I will look into it, and if I have any questions, I'll ping you.
Okay, that makes pretty much fine. And even go through this particular Spark executor tunings as well. So if you find any difficulty in understanding that, if you find any difficulties, you just let me know. I'll just try to revise that once again. It might be in the next class or so. So that will be pretty much helpful. And the next things that we'll talk about, I mean, sometime, I mean, in the last class, I just asked to refer a particular thing mainly on repartition and coalesce. So I mean, don't get me wrong. So by any chance, did you got time to refer this particular thing? Repartition and coalesce. These are wide transformations.
No.
Okay. So
Oh.
the reason why I asked you guys is because it's very important because both does almost the same tasks. So, but okay, I'll just explain you. I'll just tell you what is the difference and in what scenario we'll go for each one. And even in the interviewers, they'll ask the same question. So, have you heard about when you talk about Spark transformations? Can you just name some examples? So, you many people will say the other transformations apart from repartition and coalesce like group by key, reduce by key, sort by key, join, distinct, Cartesian, but very few will let them know about repartition and coalesce. These are also called as wide transformations, which includes extracting a data from multiple partitions, so which does lot much of shuffling of data. So now what is what they do and what is the difference between these things is, first let me talk about coalesce. If I have a data present across one partition itself. So if I have one partition, imagine 2000 records, but in real time it will be pretty much more. So I have the data only in one partition. So if you have one data present in only one partition and it's not evenly distributed, right? Because of this data is not evenly distributed, it might you're not making use of an all the available executors. So you're not making use of a Spark is a distributed framework which does the processing parallelly. You are not making use of that. So in order to overcome that, if you have a large amount of data present at one or two or very few partitions, you can be able to reduce that particular partitions into smaller chunks. Then if you submit the data to executors, it will easily be able to process because the data is distributed and it can split the data. Each executor can have this much of memory. So in that case, you can make use of and use coalesce transformation, which is mainly used to reduce the number of partitions. And imagine I have data present in two partitions. If I imagine I have data present in four partitions, I want to bring the data from four partitions to two partitions. In this case, it won't, it will keep either this or this or this or this data itself. So if I take this data, same data will be comes over here, and among this or this, one data will come over here. The data present over in these two partitions will be shuffled and stored somewhere here and here in this thing. So if I see about, there is no shuffling taking place of this data. This data will be as it is. It's not shuffling is not happening in But if someone asks which two partitions, no one knows. Even Spark Databricks, when they develop, even they too knows. Any of the two partitions will remain constant, and the shuffling will happen only in the other partitions. So this is the one thing, but in the end, you will be able to reduce the number of partitions. So this is the one key difference thing. But collage we can only use to reduce the number of partitions, and it doesn't do full shuffling of data. It keeps either of the partitions as it is that we mentioned in, if you want to get the number of partitions, and the shuffling will happen in the other partitions alone. So this is the main thing. And next comes the repartition. What repartition will do? Repartition can be used either increase or decrease. So you'll be able to increase or decrease the number of partitions using a repartition. So how we will be able to do that? Imagine I have the data present in 3 partitions, or imagine I have the data in 4 partitions. In this case, if I'm bringing the data to 2 partitions, in this case, data shuffling will happen all the 4 partitions, and imagine I have 2000, 10,000 records. So each partition can have 2500. So it does full shuffling of data. It will ensure that the new partition will be equally sized partition. So it will almost have 5,000, 5,000. So here the disadvantage is it is doing full shuffling of data, but the advantage is it is ensuring that the data size will be almost equal. It's not 100% equal, but it will ensure that the data will be almost equal across all the partitions. But in this case, data might not be equal. Depending upon which two partitions it takes and the other two shuffling happens, it will be happening. And in this case, so people will say that, so depending upon if you want to increase the number of partitions or decreasing, in that case we'll go for repartition, and it will maintain the equally sized number of partitions. So in that case we'll use repartition. If you want to reduce the number of partitions, just go for coalesce, which will maintain the unequally sized partitions. So which one will be better? Partition sized partitions is better, or unequally sized partitions better? In that case, Spark is a framework which actually does the computation in a parallelized manner. So in that case, imagine if I have a data. So imagine I have 5 executors. This is executor 1, executor 2, executor 3, executor 4, executor 5. Okay, so this is the place where the actual work will be processed. So here I have 2000, here I have 2000 records, the sample number of rows, and here I have 2, 2, 4, 6. Okay, just a minute. I'll take the 10,000 example. It will be easy for you guys to correlate. Okay, here if I take some around 4, 5, and okay, so among 10,000, these 3 has 4,500 records, and the other 4,500 will be shared among these two. Imagine in that way. So now this is the executor where the work will be launched, and these 3 will take pretty much less time to compute the 1,500 records, and these 2 will be taking a bit extra time to compute. But in the end, once if the entire computation is happened, if the result will be given back to the driver program in the Spark architecture, these 3 will wait until this work assigned to the other executors will get finished. It doesn't mean like it will only return back the driver program. So it waits the other executors to finish their task. So in this case, you will see this particular problem, will call it as a data skewness. Data skewness. So where if the data is unequally sized partitions, in these cases you will ensure that there is a problem of data skewness. So this is very much important concept, like where we might expect a question from interview, and even we need to know ways how we can tackle this data skewness, what are the various approaches, how we can avoid data skewness. So that's the I mean, that's the next thing which I'm going to cover. So that is the reason why we have to ensure that the data will be equally partitioned and the data size will also be partitioned. But one thing, do, I mean, if you ask me a question saying that, so what if the data is not equally sized partitioned? So will my job won't run? No, 100% the job will trigger and the job gets output and job gets your predicted output as well. But the thing is, internally, there is another concept like when you might have monitored the Spark application, you might have seen something called as DAG, directed acyclic graph. So these two, I mean, it's almost similar to a lineage graph, but it's a bit similar, it's a bit different. I'll just explain the difference between that. And there is a problem of data skewness. So for tomorrow, right, if you have some time, just go through this particular data structures, data frames, and RDD, and go through what exactly is a problem of data skewness, and and I'll cover in detail, or if I can cover extra the bit, because I feel that will be a burden because I already covered a lot of mathematical stuff for today. So it will be more, and then tomorrow I'll cover on these things, because this is one of the technique that we will be using as part of Spark optimization technique effectively as part of our big data. And tomorrow I'll talk about what are the various steps that we'll be covering about big data. And in general, I'll also be covering some Python, some Spark Scala assignments if that is okay for everyone. So we'll continue with that. Then accordingly, we'll plan with the other approaches, other techniques, brother. So did you got this, or you want me to repeat, or you have any query, you can just ask me.
Yeah, bro. I mean, I got it. I
Okay.
got it.
How
But
about
can
you,
you please
sister?
share the reference link for this so that I can go
Yes,
through
yes,
it?
yes. Yeah. I'll just share it. See, the the thing is, there is not one particular things, because I'll just refer. I mean, I usually refer across multiple links, but I'll share you whatever I had. I'll share you one particular book which I usually referred more often for Spark, where I referred earlier as well. So, sister, do you have any queries, or is it clear, sister?
I am little bit confused, but yeah, I'm good. I
Okay.
don't have questions as of now.
Okay, do one thing. Just go through this recording once again in your free time, or if you want, I can. Explain you once again as well. So just go through this once again, and if you have, don't think about it's a small query or big query, whatever it might be. I'll just explain in a generic way. But remember this term data skewness. This is one of the technique where every Spark developer will face this issue more oftenly, but very few will know why data skewness is happening. I'm telling you, if you run a job now, you might get a data skewness problem. Run for the second time, you might not get a data skewness problem. That's the thing. So people are like, if I restarted the job, my job was working fine. No one thinks about why data skewness happened. But very few will understand that. So if you tell this thing in an interview, so it will be pretty much comfortable for us. And there are very chances of selecting you rather than. So that's what I feel. So you just go through this particular thing. So if you have any queries, so tomorrow you can just list it down, and I'll share you some couple of links and the book that I referred more oftenly for Spark. So you can just go through that. Okay.
Yeah, okay, bro.
Yeah.
Yeah,
Okay,
sure.
sister. Yeah. That's
Thanks,
it
thanks,
for
Rajshekar.
yeah. Yeah. Thank you, Amjad. Thank
Thank,
you. Oh,
No, thank you.
so shall I stop sharing my screen?
yeah,
Yeah,
I'm
you
good.
can.
Thanks.
Yeah. Okay. Fine, brother. Then I